Welcome to another tutor short provided by the Educational Support Services Department of Lehigh Carbon Community College in Snexville, Pennsylvania, which is just outside of Allentown. These videos review key learnings for the science courses provided here at LCCC. And please remember that the Educational Support Services Department does provide walk-in tutoring 5 days a week. Let's continue our discussion on the heating curve. There is a previous video where I just described the heating curve itself, where I just review, the line here going across and describe what these represent, what these lines represent. So if you haven't looked at that and you're not familiar with this curve, I suggest you go back and look at that video first. But now that we understand what's being represented here, let's look at the types of equations that you'll use with this heating curve. And you'll see in our Chem 106 course here at LCCC, you'll be introduced to the heat equation. And you'll see it here, the heat equation represented by this Q equals M times the temperature change times a factor, in this case specific heat. So Q is the heat, and the units of heat are calories. So the heat needed, or the energy, calories also represents energy, can be calculated. Let's take the example of, we're going to take some liquid water and raise it 10 degrees centigrade or Celsius. So we're going to raise an amount of water up 10 degrees. So let's say we had 10 grams of water, and we're going to raise it up 10 degrees centigrade. And the specific heat for water is just a factor that you need to memorize, is 1 calorie per gram degree C for water. So if you one of the problems could be how much energy or how much heat is needed to be added to raise 10 grams of water 10 degrees centigrade. It'd be this equation, 10 times 10 times 1, or 100 calories. So you need 100 calories to raise water 10 grams of water 10 degrees centigrade. So that's how this heat equation is used. And the heat equation applies across this heat curve. It applies here where we're changing the temperature of liquid water, but it also applies down here where you're changing the temperature of ice, say solid ice if it's water, but the solid, if you're changing the temperature to solid, or changing the temperature of a gas. For water, it would be steam, but if you're raising, the gas temperature a couple of degrees. The only difference being, the equations look the same. The only difference is the specific heat for water or for other materials. It's a little bit different when you change the state. So as we said down here, the number was 1 for liquid water. It's a little different than 1 for a gas, and a little different for a solid down here. And depending on your course that you're taking, sometimes in the introductory courses, they'll just tell you to use 1 for water, whether you have ice, liquid water, or steam. But in other courses, they may give you the actual number for specific heat for those states, and you need to use the correct number there, or factor. So that's what you do as you're doing these changes in temperature along this curve when you're dealing with a constant state, a liquid, a gas, or a solid. However, we have something else also in this curve, which is these two conditions, the dotted line. This is when you're changing the state, either from a solid to a liquid or a liquid to a gas. And if you notice, when you're doing that, there is no temperature change. So you can't use the same equation because there's no factor here for temperature change, or there's no change in temperature. But the equation, sort of stays the same if you compare this down to, here's the equation for changing the energy required to change a solid into a liquid. Again, you have your Q, which is going to be in calories, times your mass, or going to a mass times a different constant. And if you look up above, essentially, if you take this factor out of this equation, you just have mass times some constant. And that's what you have down here. You have the mass, and the constant in this case, when you go from a solid to a liquid, is the heat of fusion for that material. And so you would look up, in a book somewhere, or you would know from your textbook. In this case, for water, heat of fusion for water is 80 calories per gram. So if you had 10 grams of water, again, like we did before, and we wanted to change ice, so if you had 10 grams of ice, converting it to liquid water, it would be times 80 calories per gram. And so it would take you 800 calories in order to melt 10 grams of ice to liquid water. Now that same type of equation applies up here when you're going from water to steam. It's the Q is the mass times now a different factor. Instead of heat of fusion, you're doing heat of vaporization. And if we use our 10 gram example again, heat of vaporization for water is 540 calories per gram. So in this case, it would take, now if we took the 10 grams of liquid water and wanted to convert it to steam, you do 10 times 540 or 5,400 calories it would take. The last thing I want to describe, you don't do this final equation very often, so I didn't show it here initially. But you can go directly from a solid here and go directly up to a gas, not going between liquid. That's called sublimation. And you might have a homework problem or something talking about sublimation. And again, you have the same kind of formula as I show down here, only now you're going to use the heat of sublimation. So it's just another factor, sublimation. And for water, if you were going to go from a solid directly to a gas, let's take that 10 grams again. The heat of sublimation for water is 620 calories per gram. So you would just do this, so it'd be 6,200 calories to do that. Now it's very rare when you do sublimation. It doesn't happen in nature very often, and so it's not as useful, say, or not as frequent that you'll come across this sublimation. And really, in everyday life, the only time you'll kind of see sublimation is if you have some solid carbon dioxide. That's dry ice. You're probably familiar with dry ice. That's actually solid. It's carbon dioxide, CO2. And if you just have a block of carbon dioxide, you'll see white smoke coming off it. It's actually going from a solid directly to a gas. And it has a sublimation factor that you could use to calculate the energy needs to do that. So hopefully that's a review that will help you when you're working on your homework in your course. Thank you.